The presence of dislocation in real crystal can be well appreciated if we consider the deformation process in a perfect crystal under the influence of an external stress, and the same is compared with experimentally measured value in real crystal. Deformations are two types, one is permanent and two is temporary. If the deformation stays even after the removal of the applied stress, then it is called permanent or plastic deformation. If we remove the applied stress, then it is deformation is goes never goes. It is called temporary deformation. Torr C equal to nu by 2 pi, and the dislocation motion is due to shear stress just onto the right dislocation center further away from its neighbor atom. The atom however simultaneously moves closer to its equilibrium distance from its neighbor atom and release almost the same amount of energy has been spent in moving the atom. As the nature of interatomic forces near the dislocation line is somewhat different from the rest of the crystal, the atoms near within the dislocation line almost completes the slip process when the next nearest neighbor are beginning to slip. Atoms away on either side of the dislocation line are not affected by the presence of motion of dislocation. Torr max equal to 2 GB by L. Energy of dislocation. Dislocation are thermodynamically unstable. Their presence always increase the free energy of the crystal. It is usually impossible to eliminate them completely, and those which remain tend to assume certain metastable configuration. Gamma equal to B by 2 PR, dE by dV equal to 1 by Torr gamma, dV equal to 2 pi R L dr, dE equal to L GB square by 4 pi dou dr by R. E equal to integral R0 to R L GB square by 4 pi dou dr by R equal to L GB square by 4 pi log R by R0 plus E0. Log R by R0 equal to 4 pi. Therefore, E equal to L GB square. Similarly, the energy of an edge location is given approximately as E equal to 1 by 1 minus V into L GB square by 4 pi log R by R0 plus E0. It is approximately equal to L GB square by 1 minus V. Thus, a curved dislocation will have a line tension T, a vector acting along the line so that T equal to dou E by dou L. So, it is equal to GB square. Slip planes and slip direction. Plastic deformation due to slip in real crystal occurs as a result of dislocation motion. Therefore, those dislocations which require the lowest energy or stress will move most readily. Further, as the energy of dislocation is proportional to square of the Burgers vector, dislocation of the shortest Burgers vector, that is those along the close packed direction, will require the least stress. The slip planes within which slip occurs are usually the most densely packed planes, which are also most widely separated. The combination of a slip direction and the plane contained it is defined as a slip system. For example, the combination of 1 1 and 1 bar 1 0 forms a slip system, but not 1 1 and 1 1 0. As the direction 1 1 0 does not lie on the 1 1 plane, the observed slip system in some FCC, BCC and HCP metals and FCC ionic crystal are listed. That is my topic. Elastic deformation. If the deformation disappears after the removal of the stress, then it is called elastic deformation. The observed stress-strain relation is quantitatively represented on the graph. It is to be noted that plastic deformation is inhomogeneous in the sense that relatively a small number of atoms actually take part in the slip process. Elastic deformation, on the other hand, affect all atoms in crystal. Here we shall study the nature of plastic deformation due to slip only and consequently obtain an expression for the critical resolved shear stress for such deformation to start. On the graph, um, we can get the elastic plastic nature of particles. These are called slip lines. They indicate that the atomic planes within the crystal have sheared with respect to one another along the slip plane, resulting in surface steps. It is generally found that the slip planes are the close packed planes, and the direction along which the slip occurs are close packed direction. Now, making use of simplified model suggested by Frankel, let us estimate the stress required to slip in the perfect crystal for the purpose. Consider two neighboring atomic planes separated by a distance d, and A is the separation between the two atoms in the same plane. Further, suppose that a stress torque is applied on the upper plane of atom so that it is displaced with respect to the lower plane of atoms by an amount x relative to its original position. For small elastic strains, the stress torque is related to the displacement x by the following equation: torque equal to nu x by d. Nu is the shear modulus, but for large displacements such as when the atoms progress an interatomic distance a, we need another representation. We know that atoms in crystal are distributed in periodic manner, and hence there exists a periodic potential inside the crystal. Consequently, as a first approximation, we can represent the stress displacement by a periodic function torque equal to k sine 2 pi x by a. K is a constant. Torque equal to k 2 pi x by a, k equal to nu a by 2 pi d, torque equal to nu a by 2 pi d sine 2 pi x by a. The shear stress torque C necessary for causing plastic deformation in a perfect crystal corresponding to the maximum amplitude of the sinusoidal wave. Therefore, torque C equal to nu a by 2 pi d. Since this is a rather a crude approach anyway, and to signification here error will be introduced if we further assume that A equal to D. So we can write the equation torque C equal to nu by 2 pi. For example, take aluminium. We make nu equal to 3 into 10 raised to 10 Newton per meter square. So that the calculated value torque C equal to 5 into 10 raised to 9 Newton per meter square. Now, in order to compare this value within the experimental one, it is necessary to resolve our tensile measurement in appropriate shear component. The stress at which slip starts in crystal depends on the relative orientation of the stress axis with respect to the slip plane and the slip direction. Consider a single crystal of cross-sectional area A under tensile stress sigma, where F is the tensile force, phi be the angle between the slip plane normal and the tensile axis, lambda be the angle between the slip direction and the tensile axis, the component of the applied force acting along the slip direction is F cos lambda, and the area of the slip plane A by cos phi. The shear stress result along the slip direction is then torque equal to F cos lambda by A by cos phi equal to F by A cos phi cos lambda equal to sigma cos phi cos lambda. This resolved shear stress when reaches a critical value is called the critical resolved shear stress CRSS. For plastic deformation to start, this is given by torque C equal to sigma C cos phi cos lambda. For aluminium, from the typical measurement value of sigma C, we find that torque C approximately equal to 10 raised to 7 Newton per meter square. This gives us a difference of about 3 order of magnitude between the measured and calculated value of torsi. In other words, a real crystal deforms at a much lower stress and perfected by a model which is based on perfect crystal. This disparity can be explained on the basis of presence of dislocation in real crystal.